Now today we are going to see the wave function and its physical significance in the quantum mechanics. Now what is a wave function? A wave function, a physical situation in quantum mechanics, is represented by a function called as a wave function. It is denoted by psi. It accounts for the wave-like properties of particles. So wave function is obtained by solving Schrodinger's wave equation. Now what is a Schrodinger's wave equation? To solve the Schrodinger's wave equation, it is required to know potential energy of a particle, initial conditions and boundary conditions. So what exactly is a wave functions? Now we have seen previously the de Broglie's hypothesis, Heisenberg's uncertainty principle. Significance of Heisenberg's uncertainty principle determines the probability of finding the position of a particle or the momentum of a particle. So the probability has to have some wave function. So in order to do that, we are going to see the wave function. What is it called? A physical situation. Any physical situation in quantum mechanics is represented by a function, wave function psi. It is denoted by psi. And wave function can be obtained using a Schrodinger's wave equation. Schrodinger is the name of a scientist who has worked on it and led to the solutions for many of the problems. To solve the Schrodinger's equation, it is required to know the potential energy of a particle. What is the potential of a potential energy of a particle, initial conditions and boundary conditions. Now we will see there are many such derivations which we are going to see in the quantum mechanics. Before going to that, we should have this minimum requirements. What is a wave function? Because next topic we will go with the time independent Schrodinger's wave equation. So all these things requires a wave function. So before going to another topic, we should know what exactly is a wave function. Therefore we are discussing all these things. Now what is the physical significance of a wave function? What is a psi? What is its importance? What is the requirement to study all these things? Is it required? And how the psi can give the solutions for many of the problems? All this can be determined. Now we will see the physical significance of a wave function. If psi is a wave function associated with a particle, then mod psi whole square is a probability of finding a particle in the unit volume. See, the probability has come into picture. This is just because of Heisenberg's uncertainty principle. We are getting the term as probability, means everything in the quantum mechanics will be dealt with the probability, and in order to deal with probability we should have a wave function, and that wave function is nothing but a psi. Therefore if psi is a wave function associated with a particle, that means see how the wave function is being given to a particle and solving these equations which led to the solutions of the many of the problems. Now we are associating a wave function to a particle, therefore mod psi whole square is a probability of finding a particle in a unit volume. Now next is probability of finding a particle in certain elementary volume d tau is given by mod psi whole square d tau. Thus mod psi square is a probability density. That means what is a probability density? Density is mass per unit volume. So similarly here, when psi is associated with a particle, that means the wave function is associated with a particle which is lying in a volume element of d tau. Then mod psi whole square is called as a probability density, because we are seeing in an elementary volume. So the probability of finding an event is real and a positive quantity. In the case of complex functions, the probability density is mod psi square is equal to, how we deal with mod psi whole square is psi star psi, where psi is a complex conjugate of psi. You should be good at all this terminology in order to go with further theorems or derivations in the quantum mechanics. So before going to all those things, we should have the knowledge of probability density, normalization function, complex conjugates, and little amount of knowledge of complex numbers. So mod psi whole square is nothing but psi star psi, which is nothing but psi star is a complex conjugate of psi. Next, what is normalization? The probability of finding a particle having a wave function psi in a volume d tau is mod psi square d tau. We have seen that mod psi whole square d tau is nothing but a probability density, or you have seen in this. See here, mod psi whole square is nothing but a probability density. Now what is normalization? The probability of finding a particle having a wave function psi in the volume d tau is mod psi square d tau. If it is certain that the particle is present in a finite volume tau, then we give the equation as integral of mod psi whole square d tau is equal to 1. The lower limit and upper limit 0 to tau. That means the finite volume is from where what is the lower limit and upper limits of a finite volume tau is nothing but 0 to infinity. Mod psi whole square d tau is equal to 1. Always remember, probability means 1 means definitely it will be within. 1 means 100% assurance. The probability, if you look at the probability conditions, the probability of finding a particle, probability of finding a particle within that element is 1 means 100% that particle will be within the box of finite volume d tau. So always remember, possibility 1 means 100% chances, probability 0 means 100%, 0% chances. That means it will not be available. So here, if a particle is present, if it is certain, we know that there is a particle means the probability will be coming to 1. If it is certain that particle is present in an infinite volume, here itself we are giving a statement that it will be there in the volume tau, means it will be integral of 0 to tau mod psi whole square d tau is equal to 1. That means it is there. The process of integrating the square of a wave function in a suitable limits and equating it to a unity value of constant involved the wave function is estimated. So always integrating the square of a wave function within the suitable limits and equating to unity the value of constant involved in the wave function is estimated. So we can see that constant involved, the value of constant involved in the wave function can be estimated. The constant value is substituted in the wave function, and this process is called as a normalization. The process of doing such type of equations is called as a normalization. What are the properties of wave functions? The acceptable wave function has to possess psi is a single valued everywhere, psi is a finite everywhere, psi and its first derivatives with respect to its variables are continuous everywhere, and for bound state psi must vanish at potential boundary and outside. If psi star is a complex function, then psi star psi must also vanish at potential boundaries and outside. The wave function which satisfies above 4 properties are called as eigenfunctions. So you have to deal with these eigenvalues and eigenfunctions. So before going to start with eigenfunctions, these 4 conditions the wave function should be satisfied. That is, psi should be a single valued everywhere, psi is finite everywhere, and psi and its first order derivatives. You know what is meant by first order derivatives. dx by dt, this is first order derivative. Second order derivative means d square x by dt square. So psi and its first order derivatives with respect to variables are continuous everywhere. For a bound state, psi must vanish at potential boundary and outside. If psi star is a complex conjugate, then psi star psi must also vanish at a potential boundary and outside. The wave function which satisfies all these 4 conditions, then such function is called as a eigenfunction. Now we will see the Max-Born's interpretation of the wave function. What is Max-Born's interpretation of a wave function? A satisfactory interpretation of a wave function psi is associated with a moving particle which was given by Max Born in 1926. That means this Max Born approximations were given in 1926 by Max Born. Max Born postulated that the square of the magnitude of the wave function mod psi whole square evaluated at a particular point represents the probability of finding a particle at that point. The same thing, probability is been coming into picture, the probability of finding a particle at that point. Psi star is called as probability density, mod psi whole square is called as a probability density, and psi is called as a probability amplitude. According to Max Born interpretation, the probability of finding a particle in the space is given by integral of minus infinity to plus infinity mod psi whole square dv is equal to 1. Why the limits are taken here as minus infinity and plus infinity is, it is in the space. So the limits changes to minus infinity to plus infinity. Probability, definitely the particle will be within the space, therefore it is equal to 1. So the normalized wave function must be finite, single valued and continuous everywhere. So these are the Max Born's interpretations of a wave function. For a in quantum mechanics, we will deal everything with the wave function and eigenvalues. Hope you understand that. Then these are the Max Born's interpretation of the wave function. Thank you.